we have seen how to expand expressions like this. We would end up with x squared plus 2x subtract x subtract 2, which we can simplify to x squared plus x subtract 2. Expanding these brackets has turned out to be a pretty straightforward process. But suppose that we were starting with the expanded form and needed to put this back into its brackets. In other words, suppose we needed to factorize this expression. That presents a few extra challenges. So the kinds of expressions that we're interested in factorizing are quadratic expressions. These are expressions of the form ax squared plus bx plus c, where the a, the b and the c are any numbers. So, for example, 3x squared plus 2x plus 1 is a quadratic expression with an a of 3, a b of 2 and a c of 1. 2x squared subtract x subtract 4 has an a of 2, a b of minus 1 and a c of minus 4. No need for these numbers to all be positive. The expression 4x squared plus 3 is a quadratic expression with an a of 4, a b of 0 and a c of 3. 7x squared plus x is a quadratic expression with an a of 7 and a b of 1. The c is 0 in this case. However, if we were to look at the expression x minus 4 with an a of 0, a b of 1 and a c of negative 4, this we would not count as a quadratic expression. We need to have a term in x squared. In other words, we're only going to be interested in the situation where a is not 0. Now we are going to try and factorize expressions like this, and throughout this unit when we talk about factorizing, we are talking about putting these things into brackets where all of the coefficients of x and all of the numbers are integers. Factorisation does not necessarily mean that those numbers have to be integers, but that's what we are going to mean when we talk about this process. So here is our first quadratic expression to factorise. 2x squared subtract 5x. And this does not require any new methods. We can just factorise a common term. There is an x in both pieces. We could factorise that out, leaving 2x subtract 5. If there is a common factor, we can factorise it out in the usual way. In this example, we don't have any common factors. So we are going to have to try to write x squared subtract 3x subtract 4 as 2 brackets multiplied together. Now my main recommendation for you is just to see if you can work out what the answer is pretty much by looking at the quadratic expression, just trying to do it on sight, bearing in mind that we are only interested in factorizations which involve whole numbers. Now we have 1x squared in this expression, which means that the x pieces in both of our brackets must again just be 1x in each bracket. It's the only way we can multiply these pieces together to get 1x squared. Similarly, the numbers at the end of the bracket must be multiplied together to come to negative 4. So we don't have many options. We could either have a 1 and a 4, or a 2 and a 2. Of course we could have a 4 or a 1, but that's the same as the first situation in reverse. Because they multiply together to give us negative 4, we must have different signs in the brackets. Either we have a plus in the first bracket and a minus in the second, or the other way round, a negative in the first bracket, a positive in the second. Now we have very few possibilities, so it usually is the best thing just to consider them and see what will work, and it doesn't take an awful lot of thought to realize that we must have a negative 4 and a plus 1, because x times x gives us the x squared. Negative 4 times x will have negative 4x's, but then we'll have x times 1, a positive x, giving us negative 3x's altogether, and negative 4 times 1, giving us the negative 4. Let us see if we can use this idea of factoration by sight to do this next example. We have to factorise x squared plus 5x plus 6. Now again, our two brackets must both have a single x at the beginning of them. It's the only way we're going to be able to multiply out these brackets to get a single x squared. The two numbers must multiply together to give us 6. So what are our options? 1 and 6, 2 and 3. They must both have the same sign, either both plus or both minus, because they multiply together to give us plus 6. Now how can we get these 5x's? A little moment's thought show us that the only combination that will work is the x plus 2 and x plus 3. X times x is x squared. Then we will have 2x and another 3x, giving us the 5x's, and then 2 times 3 is 6. One of the things which has made the factorisation on site not too difficult so far is the fact that we've always just had a single x squared. However, in this case we have 2x squareds. How can we deal with that? Well, this time, when we put this as the product of two bracketed terms, how can we make a 2x squared? We must have 2x at the start of one bracket and x at the start of another bracket. This has been made a little bit easier because of the fact that 2 is a prime number. There's only one way we can split it up. And similarly, this 5 on the end is also prime, so there are not many possibilities for what we can have here. Either the first number is a 1 and the last is a 5, or the other way around. We also have the same issue that we had before, in that because the number is negative 5, we must have one positive and one negative number. But once again, it doesn't take an awful lot of thought to realise that we must have 2x subtract 1 and x plus 5. Because how do we make this 9x? 2x times 5 is 10x, and then negative 1 times x is taking one of them away, giving us this 9x. In this example, a lot of those nice features have been taken away from us. We need to try and factorise 6x squared plus x subtract 12. Now we have a little bit of a problem, because there's several ways we could split this 6 up. Maybe this first bracket begins with a 6x, in which case this bracket would begin with an x. Or maybe this bracket begins with a 3x, in which case this one would have to begin with 2x. The numbers on the end have to multiply to negative 12. So we have again this sign difference. One must be a plus and the other a minus. But what are the numbers on the end? There are lots of ways we could make 12. We might have a 1 and a 12. We might have a 2 and a 6. We might have a 3 and a 4. And we have to consider the situations where these are the other way around as well. Suddenly there are so many possibilities, it becomes a little trickier to do things like this on site. Now there is a formal method for factorising quadratic expressions. When we don't need it, factorising by sight is much quicker. But let's see how we can use that formal method to factorise an expression like this. Now this method may well have a nice formal name of which I'm unaware. I just call it the ACB method for factorising quadratics. Our first step is to just write down the values of a, b and c, and also the value of a times c. We then need to find all of the possible factorizations of AC. Then we find the factorisation m times n of AC, such that m plus n is b. We rewrite our original quadratic as ax squared plus m plus n lots of x plus c, and expand that bracket to give us ax squared plus mx plus nx plus c. We factorise the first two terms, the ax squared plus mx, and the last two terms, the nx plus c. Once we've done that, each term should contain the same bracketed term, which can now be factorised out. Now that is a long and complicated method if we don't hang it on an example. Let's run our previous example through this method and see that actually it's not so complicated. So our first step was to write down the values of a, b and c. So we have an a of 6, a b of 1 and a c of negative 12. We also had to write down the value of a times c. 6 times negative 12 is negative 72. Step 2 is to find all of the possible factorizations of AC. By factorizations of AC, we mean factorizations of the number AC, negative 72, into two smaller factors. Now we have lots of possibilities here. Negative 72 could be written as negative 1 times 72. It could be written as negative 2 times 36. It could be written as negative 3 times 24. It could be written as negative 4 times 18. It could be written as negative 6 times 12. It could be written as negative 8 times 9. And then by symmetry, we also have that it is negative 9 times 8, negative 12 times 6, negative 18 times 4, negative 24 times 3, negative 36 times 2, and negative 72 times 1. That is a lot of options. You will see that it is not always necessary to write all of them down. However, in this case, we have found all of the factorizations of AC into two factors. Next step, find the factorization mn of AC such that m plus n is b. So what we need to do is add together the two numbers in our factorizations and see if we get b. So in the first one, if we did negative 1 plus 72, we would get 71. 71 is not b, which is 1, so this one is no good to us. Next one, negative 2 plus 36, that gives us 34. That's not 1 either. And so on. Now, you can see we don't have to check all of these because it's incredibly obvious that most of them are not going to add up to 1. In fact, we can very easily see which one is going to add up to 1. Negative 8 plus 9 is 1, which is b, so this is the one we are interested in. Step 4 is to rewrite the original quadratic expression, but using m plus n in the place of b. So our original quadratic expression was 6x squared plus x subtract 12. Now we have to write that as 6x squared, and instead of b, instead of 1, we have to write negative 8 plus 9. That's how many x's we have got. Subtract 12, our c stays the same. And also we are told to expand that bracket. So we have 6x squared subtract 8x plus 9x subtract 12. Step 5 is to factorize the first two terms and the last two terms. The first two terms are the 6x squared subtract 8x. So if we just factorize these pieces, what is common to both pieces? Well, they're both multiples of 2 and they both have an x in them. What would that leave us? That would leave us with 3x subtract 4. We also have to factorize this second two terms. What's common to both of those? Only a 3. If we factorize out a 3, we have 3x subtract 4. Step 6, our final step, says that each term should contain the same bracketed term, which can now be factorized out. And each term does contain the same bracketed term, the 3x subtract 4. So if we factorize out the thing which is common to both terms, this 3x subtract 4, what are we left with? The first piece leaves us with 2x, the second piece leaves us with plus 3, and we now have our factorization of 6x squared plus x subtract 12. This formal method, as you can see, involves quite a lot of steps. It is much better to factorize expressions on site when you can. I would therefore recommend quite a lot of practice of this until it is something you're able to do pretty much by second nature. At first sight, this example looks like it should be easier, because the coefficient of x squared, being 5, is a prime number. The number on the end, the 3, is also a prime number. So there shouldn't be many ways we can split this up. We would have to have a 5x at the beginning of the first bracket and an x at the beginning of the second bracket. And then the numbers, either there's a 1 here and there's a 3 here, or there's a 3 here and a 1 here. And because the sign of the number on the end is negative, either we have a plus and a minus, or a minus and a plus. There are a few options, but not that many, and we could quickly check them out and see what happens. However, I can assure you that whatever you try from these 4 options, it will not work. Let's just try one of them. For example, if we have 5x plus 1 and x subtract 3, then when we expand that, we get 5x times x, which is 5x squared. We would then have 5x times negative 3, subtract 15x, plus an x, subtract 3. Well, we have got our 5x squared on the beginning. Unfortunately, we've now got negative 14x, subtract 3, so that has not worked. And you can try all of the other possibilities. None of them are going to work. The simple fact is, not all quadratic expressions will factorize using integers. How can we tell this in advance? Let me introduce you to an idea we're going to meet a lot later on, called the discriminant. What do we mean by the discriminant of a quadratic expression? It has the symbol Greek capital delta. What we mean by the discriminant is b squared subtract 4 times a times c. So in our case, we have a discriminant of b squared, b is negative 1, subtract 4 times a, which is 5, times c, which is negative 3. This comes to 61. Now the way to tell if a quadratic expression is going to factorize or not is to look at its discriminant and see if it is a square number. 61 is not square, and if you have a discriminant which is not a square number, your quadratic expression will not factorize. So in this case, it is not going to be possible to write this quadratic expression in any form simpler than it is already written. In this example, we have to factorize the expression x squared subtract 4. There is no x term in this quadratic expression. So, if we have to write that as the product of 2 brackets, we must have an x at the beginning of both of them, and the 2 numbers must multiply to negative 4, meaning that we either have a 1 and a 4, or a 2 and a 2, and they must be of different signs. Well, if we had the 1 and the 4, whichever arrangement of plus or minuses we had, the brackets would multiply out to give us a term in x, which is what we don't want. So they must be the negative 2 and the positive 2. Let's just check that. X subtract 2, x plus 2, x times x is x squared. Then we would have plus 2x, subtract 2x, subtract 4. Yes, we really do get x squared subtract 4. This is an example of a situation called the difference of 2 squares. Now the difference of 2 squares comes up quite a lot in this course, and it is very well worth recognizing it whenever you can. In general, if we have an expression such as a squared subtract b squared, whatever a and b may be, they may be numbers, they may be variables, this will always factorize as a subtract b, a plus b. And you'll be surprised about the number of times in which recognizing an expression like this so that you can factorize it in this way would occur throughout the course.